Hi everyone. So we spent the first half of class talking about difference equations where time is discrete. But many real-world systems have continuous time, for which differential equations are more appropriate. As one of the prereqs of this class is MATC58, which is ordinary differential equations, we're not going to spend too much time on it, but we are going to review some of the important concepts. So let's start by defining everything formally, which is a standard thing. So this is 4.1 in the Linda Allen's textbook. So what is a differential equation? So a differential equation of order n is an equation, let's write it as f of x, the first derivative with respect to t, the second derivative, and so on, all the way through the nth derivative, which is why this is of order n. D to the n x over dt to the n, as well as possibly dependent on t, is equal to 0, where x is a function of t. Okay, so this is the standard setup, and of course there are a couple other notations that we might use. One of the other ones which we'll see, which I will use fairly often in this class, is going to be the dot notation, since we're taking derivatives with respect to time. Yeah, so I'll be using those two notations interchangeably. So now, as with difference equations, we have many of the same concepts like autonomous, non-autonomous, linear, nonlinear, homogeneous, and things like that. So we covered this in one of our early lectures, but I'm just going to review all these concepts again formally. So if an ODE, so ordinary differential equation, does not depend explicitly on time, then we call it autonomous. So same as with difference equations. So that is to say f of x, x dot, x to the n, t is the same as, has no dependence on time. When it's autonomous. When it is autonomous. Otherwise, well, we use the same terminology, it's non-autonomous. And of course, we can also define linear in the same way. And instead of being linear with respect to x of t plus 1, t plus x of t plus 2, etc., we're going to have it be linear in terms of all the derivatives. So in ODE, well, that can be rewritten as d to the n x, d to the t n, plus a1 of t. So this is some coefficient that's a function of t, but not of x. d to the n minus 1 x, dt to the n minus 1. The sum all the way to a n minus 1 of t, dx dt, plus a n of t x is equal to g of t. So that is linear. Otherwise, nonlinear. Okay, so, and of course, for a linear differential equation, we can also define whether it's homogeneous or not. So, if given a linear ODE of the form above, we have g of t is identically 0, then it is homogeneous. So it's a term that doesn't include a x or a derivative of x. Otherwise, well, we call it non-homogeneous. And of course, we have the exact same definitions for systems. So let's write this all out formally. I apologize for this being a bit slow. You can probably skip this video if you still remember all of your terminology and definitions from MATC58. So a first order system is one that can be written as, I'm going to write it in matrix form, just because we'll be dealing a lot with matrices in the same way as we did with the difference equations. So this is some function of x of t, where the t here is a vector. So where x of t is equal to little x1 of t through little xn of t, and f, well, that is a bunch of functions f1 through fn, and each of our fi's is a function of x1 of t, x2 of t, all the way through xn of t, and possibly t itself. So functions of all different variables. And we have the same definitions of autonomous and linear, homogeneous, and all that for systems of equations. So a first order system is autonomous if f of x of t is the same, has no dependence, has no direct dependence on t. So i.e. does not depend explicitly on t, though of course it will have a dependence on t through through x. Does not depend explicitly on t. Non-autonomous otherwise. And it's linear if we can write it in matrix form, like as a matrix instead of just as if the function f can be written as a matrix, basically. A first order system is linear if dx dt, and this is of course a function of t, is equal to a of t, x of t, plus g of t. Oh, sorry. Where a of t is a matrix. So this is a11 of t, each of these coefficients, a1n of all the way through a1n of t, down to an1 of t, through ann of t. So it's an n by n matrix of coefficients that may depend on t. And g of t is, well, constants that may depend on t. I really shouldn't say constants, but they only depend on t and they don't depend on x, which is the important part here. So otherwise, well, of course, we call it nonlinear. Okay, and of course, a linear first order system is homogeneous if g of t is, well, the zero vector, and otherwise non-homogeneous. Okay, and let's finish off with giving one theorem, which we're not going to prove in this class since we proved it in, or at least some B44 classes will have proved this. So this is theorem 4.1 in your textbook. And it has two different parts, one for ODEs and another for systems of first order ODEs. So let's use the other notation just to make life easier. So a1 of t, x to the n minus 1, all the way through a n minus 1 of t x dot plus a n of t x. That's equal to g of t. And we have an x of t naught is equal to x naught. X dot of t naught is equal to x1. And x to the n minus 1 of t naught is equal to x n minus 1 initial conditions. Well, then if all of our functions, if all of our AIs for I equal 1, 2 through n minus 1, and G are continuous on an open interval, well, if they're all continuous on some open interval I containing some point t, point t naught, then there exists a unique solution locally. Solution x of t on I. So there is some function x that does satisfy these things, and so that's an existence proof. And similarly, there's something comparable for systems of first-order ODEs. So x dot of t equal to a of t x of t plus g of t. And we have x of t naught is equal to some vector x naught initial conditions. When if a of t and g of t are again continuous on an open interval I containing t naught, when there exists a unique solution. So I'm not going to prove this. It should have been proven in a differential equations class. If you don't remember it, you should go back and look there. And I'm just going to give a single example of a differential equation. You guys should be very familiar with these, but just as a reminder, let's say that we have d squared x over dt squared plus 3 over t dx dt plus x over t squared is equal to 0. So this is a differential equation. We have x of 1 is equal to 0, and x dot of 1 is equal to 1 are our initial conditions. So, well, we know that all coefficients are continuous on the positive real axis, since are continuous on the positive real axis. So there exist unique solutions. And we'll be going over this a bit more in the next video, but we can find a general solution, x gen of t, which is equal to c1 t inverse plus c2 t inverse log, natural log of t. And you can plug this back in, and you'll see that this does get you what you want. And if you have a general solution, well, let's go ahead and take the derivative since we'll need this in a moment. c1 t to the minus 2 plus c2 t to the minus 2 minus c2 t to the minus 2 natural log of t. So this is by the product rule. And we can solve the initial value problem by plugging stuff in. So x of 1 is equal to 0, and that happens if you plug in 1 into log of t, that's 0. So this thing becomes 0. And we are just left with is equal to c1. And we have x dot of 1. X dot of 1 is equal to 1, which is equal to minus c1 plus c2, which implies that c2 is equal to 1, which implies that the solution, if you already knew the general solution, we could solve for the initial value problem, and x of t is equal to t inverse natural log of t. Okay, so that was a really quick introduction to review of differential equations. In the next video, we'll focus in and review some facts about linear differential equations, and especially solving linear differential equations with constant coefficients by using the characteristic polynomial. So the exact same sort of thing we were doing for the difference equations using the characteristic polynomial, except the solutions will be a little bit different.